All right, our objectives is to look at something called the mean value theorem for integrals. Now, I need to emphasize this is MVT for integration, for integrals. This is different than the MVT we studied last semester. In general, if a question on the AP exam asks you about MVT, they're talking about MVT for differentiation. This is MVT for integration. We'll also look at something called the average value of a function on a closed interval. And finally, be able to understand and use FTC in accumulation problems. So let's start off with MVT for integrals. MVT for integrals. We have seen that the area, that's this region under this curve here, we have seen that the area of the region under the curve is greater than the area of inscribed rectangles. That means they're all underneath. And it's less than the area of circumscribed rectangles. That means all the rectangles are up above. The mean value theorem for integrals states that somewhere between the inscribed and circumscribed rectangles, there is a rectangle whose area is precisely the area under the curve. Let me explain what I mean by that using this picture right here. So it's kind of hard to see, but I'm going to kind of shade this in. So you see this area that I've tried to shade in here with my finger. That is the exact area under the curve. And let's say that the exact area, just to keep it simple, is 10. The claim is that there's some rectangle here. There's some rectangle for some value C. Guess what the area of that rectangle is going to be? 10. Okay? That's what this theorem is saying. That's the big idea. The big idea is that there's some value of C in between A and B for which the area of that rectangle is equal to exactly the area under the curve. And that's what we call the mean value theorem for integrals. Here is the formula. This is an important slide. Oh, do you guys want the PowerPoint? Would you guys like to have that? Let me give that to you right now. Sorry, I should have done this already. I've got it ready, but I need to make it shareable. Okay, copy link. It is now in the chat. There you go. If you want the presentation, and I'll post the presentation later on this week, but there you go. All right. Okay, so this slide is an important slide. This is MVT for integrals, and here's what it says. On the left-hand side, you've got the definite integral. And by the way, when you evaluate a definite integral, you're going to get a numeric answer like 10. On the right-hand side, this side over here, notice that it says f of c equal, oops, it doesn't say equal. It says f of c parenthesis b minus a. This is simply the length of the interval. It's the length of the interval. It's this length right here. And guess what this is? That's the height of the rectangle. So again, here's what the mean value theorem for integrals says. The exact area under the curve is equal to the, well, that's the base times the height. That's the height of it. That's the area of a rectangle. Let's say rectangle area. Okay, so here it is symbolically. Here it is in picture form. Now, usually these theorems, they seem very underwhelming when you look at them. It's when you actually start working them out that things get interesting. So let's look at our first example. In this particular example, it says, since g of x equals x squared plus 1 is continuous on the interval -1 to 2, the mean value theorem for integrals says that there is some number c on that interval such that the integral from a to b, and by the way, here's your a and here's your b, the integral of that function over that interval has to equal the value of the function for some value c times the distance between b and c. I'm sorry, between b and a. Okie dokie. So what in the world does that mean? Here's what it means. Let me show you a picture. So this red curve right here is the actual curve, x squared plus 1. I just did it in Desmos. And so what we're talking about is going from -1 to 2. Well, here's -1, so we're going from right here all the way to 2, which is right here. We want to know, first of all, we want to figure out what this area is. So what I'm trying to do here is give you the geometric representation first, okay? And let's do that with this. We want to integrate from -1 to 2 of x squared plus 1 dx. All right, so we want to figure out what the antiderivative is for x squared plus 1. Well, that'd be x to the third over 1 plus, I'm sorry, not 1 over 3, plus x. That's the antiderivative. And we need to evaluate that from -1 to 2. Okie dokie. So now I've got to do a little computation. I'm not going to show all the work, but I'll show most of the work. So what I need to do here is I need to do 2 to the third divided by 3 plus 2. That's the first part. That's f of b minus, and then I got to plug in -1. So I got to do -1 to the third over 3 plus, and then -1. That's how I'm going to figure out what this answer is. Does anybody happen to know what that integral is? Has anyone plugged that into their calculator yet? Well, the answer turns out to be 6, okay? You can check that if you want with your calculator. In fact, that'd be great if someone would check that, but I'm pretty confident that the answer is 6. I picked that on purpose because I wanted it to come out to be a nice number. Now, this 6 represents what? The exact area under this curve from -1 to 2. That's the exact area. I picked it because it was a nice number. Now, what I claim is there has to be some rectangle for some value of c. Remember, that's what we're going to try to figure out, where that's true. So here comes the key part. I'm now going to use this formula right here. I'm going to say 6, which is the value of the definite integral, is equal to g of c times, and what was b? Well, it was 2. And what was a? -1. By the way, when you minus a negative, you're going to get +1. And 1 plus 2 is 3. And then when I divide both sides by 3, you're going to get, I think, 2. So the question is, when is g of c equal to 2? Well, that might seem like a hard question, particularly if you didn't have this graph. Well, what is f of x? Well, it's x squared plus 1. So I'll switch colors again. So that means 2 has to be equal to x squared plus 1. In other words, x squared has to equal 1. And when is x squared equal to 1? And? Well, it's equal to plus or minus 1. Because -1 times -1 is 1. And 1 times 1 is also 1. So it turns out that in this example, there are 2 values of c that will make that true. In fact, let me draw those for you right now. I'm going to do the first one in green. So I said c was equal to -1 or +1. So over here, this is where c is -1. I'm going to draw a rectangle just like this right here. Now, what's the base length of this rectangle? Well, it's still 3, right? Because I'm going from -1 to 2. That's 3. What's the height of this rectangle? Now, you guys may not be able to see it there, but it says 2. Guess what 2 times 3 is? It's 6, which was the exact area we were talking about earlier, isn't it? Now I'm going to draw another rectangle. This time I'll do purple. This time I'm going to draw my rectangle. C here is 1. Over here was c equaling -1. Here's C is equal. So here's the height right here. Oh, wait a minute. Wow, interesting. Look what you have. You still have a rectangle with a width of 3, and guess what the height is again? It's still 2. So I don't know if you remember this about the mean value theorem for differentiation, but it turns out that this value of C does not have to be unique. In many examples, it is. This is an example where there were 2 values of C where it was true. Did you know there could be actually hundreds of values of C? And I know you're thinking, oh my gosh, please don't give us, that's not my goal. I just want to let you know, C is not unique. In fact, let me go back real quick to this theorem. It says there exists a number C. It doesn't tell you what it is. It also doesn't tell you how many there are. So be careful. Don't make the mistake of saying, oh, Mr. Allen, the answer for this problem is C equals 1. Well, you're almost there. You missed half the answers, though. The other half the answer is -1. Comments or questions on this one? Now, would you guys agree this is one that we could definitely do without a calculator? For sure, right? Let's do now one with a calculator. In fact, I'm going to give you a little bit of a head start. I'm going to kind of pause now, and I'm going to go ahead and let you maybe think about this for a second. I'm going to kind of get my ducks in a row too. And here's what the question, it's the exact same question. It's just got a different function and a different A and B value. It says, find the value of C guaranteed by the mean value theorem for integrals for the function f of x equals cosine of x. So there's our good friend cosine. And the interval is going to be -π/3 to π/3. And I'm encouraging you to use a calculator. So have fun. I'm going to give you, 3 minutes might do it. All right, so I think we're at that 3-minute mark, or pretty close to it. Gaia has brought up a question. Gaia, I assume you're talking about example number 1. You said you did not get 6 for the answer. Did anyone?
I did get 6.
Oh,
the calculator said
I'm
6.
so sorry, Guy. I misunderstood. Thank you very much for confirming that. I thought you were saying I screwed something up. I started getting nervous there because when Gaia says there's something wrong, she's usually right. So excellent. Okay, thank you, Gaia. All right, so so this one, I encourage you to use a calculator. And again, I would just like to reiterate that to get good at math, you need to do the math. I mean, it's one thing to watch someone else do math and be like, oh yeah, that makes sense. And then it's another thing to actually do it. So the first thing that you could do on a problem like this is just simply sketch this curve. Now, this particular curve is the cosine function, which you're pretty familiar with, I hope. And we're just going over this interval. And so we're starting over here at negative pi over 3, and we're going to go over here to pi over 3. And it turns out that the curve basically looks something like this. Okay, I didn't do a very good job there. It should have peaked up there at the y-axis, but it looks something like this. So we're trying to figure out, so this is the area we've got. We're trying to figure out what value of c is guaranteed by the mean value theorem. Now, it turns out that the integral from negative pi over 3 to pi over 3 of f of x dx is the square root of 3. We could have actually done this by hand because the antiderivative of cosine is sine, and you could have evaluated it that way. That's the exact value. If you want the decimal approximation, since I encouraged you to use a calculator, you may have done that. And that, if you want that, there you go. Obviously, this answer's a little better probably, right? But this is very accurate, so that's fine. So now we need to say, you know, when is the square root of 3 going to be equal to f of c times this, oops, not the square root there. That's going to be pi over 3. Pi over 3 minus negative pi over 3. In other words, this square root of 3 is going to be equal to, that would be what, 2 pi over 3? 2 pi, I keep wanting to write square root of f of c. And then we can multiply both sides by that, and I think that would give us like 3 radical 3 over 2 pi has to equal f of c. Anyways, things are getting kind of ugly here, aren't they? So what do? I'll tell you what you do. You graph this function with your graphing calculator, which is exactly what I did. And then guess what you do? You will graph the line y equals 3 radical 3 over 2 pi. And it's going to give you a horizontal line that looks something like this. Right? And then what you need to do, or this is one, I guess I need to be careful. There's more than one way to do it. You can actually do this with your calculator without graphing it. This is probably the easiest way, though. It turns out that there are 2 places. In fact, let me tell you what those are. This particular place right here is c equaling negative 0.597. And then this one over here is c equaling plus 0.597. And notice I'm going out to just 3 decimal places because that's all the AP exam is going to require us to do. Anyways, there's your answers. There's 2 of them again. It doesn't always have to be 2, but I want to just emphasize that because I think it's important for you guys to know. Comments or questions? If you need to see something on the calculator, this would be a great time to ask. Otherwise, I will move on.
Which equation did you type into the calculator to get the square root of 3?
I didn't. I mean, you can. I mean, this is the decimal you'll get. To get the square root of 3, you would do it by hand.
Oh, okay. I mean, like, did you just type in, so you didn't include cosine when you typed it into your calculator, or did you?
Yeah, you would.
Okay.
Yeah. I just wrote f of x because that's what f of x is. But yes, you could certainly, I'll change that right now. Instead of writing f of x here, you could have, and actually that's what it is, you know, that's the cosine of x. That would go right there. Oh, by the way, if for some reason you did not get this, double check that you're in radians. If you're in degrees, you will not get this. In fact, in this class, if you forget to change from degrees back to radians, they're all wrong. And that will happen also on the AP exam. I know that sounds like I'm being a big bummer, but it's true. You need to know what your calculator is doing. It's a tool. And if the tool is not set up correctly, you'll get incorrect answers. And that would be very sad, wouldn't it?
Very important reminder. Thank you for that.
You are very welcome. And I'm just going to tell you guys right now, in this class, Calc AB, the only mode you're ever going to be in is radians. Okay, the only exception to that would be next year if you take Calc BC, things might change. By the way, did you guys happen to hear that they're changing the SAT? Who are my juniors? You might want to Google that. They're kind of changing the SAT big time. They're basically saying that colleges are basically starting the year after next be looking at your AP scores for admission. Just to let you know. So here's a poll for you, please, if you don't mind figuring that out for me and giving me some answers, and then we'll move on to the next thing. Real quick poll.
Mr. Allen, I have a question.
Yeah.
Okay, so when you got the 0.597,
Yeah.
you plug that into your calculator, but how would you do that, like, if you didn't have the calculator? Would you just plug this?
You would not be able to do this one without a calculator.
Oh, okay.
Yeah, so
But so are you plugging in, like, the 3 square root of 3 over 2 pi into cosine?
So here, yeah, that's exactly right. So what I'm doing here, Rachel, is on my graphing calculator, I would have had the graph of cosine already in there.
Yeah.
And it's on my graph.
Mm-hmm.
And then what you do is once I figured this number here, this is what f of c has to equal. This is the height, if you will, of the rectangle. So all I did then is I graphed this equation here, which is a line. It's a horizontal line. It's a number, right? Y equals, like in this case, some weird transcendental number, but it could be y equals 2, for example, in the last example we did. And then all I did is I used the intersect feature to figure that out.
Okay.
Now, the other way we could have done this with the calculator is you could have used arc cosine or inverse cosine, set it equal to, anyways, arc cosine of this will also give you those answers. But you got to be careful. The calculator is only going to give you the positive answer, and there is a negative answer. And this is the thing that, these are the things that quote unquote differentiate really good calculus students and not great calculus students, is that attention to detail. So be careful with that. And by the way, Mr. Allen's guilty of not paying attention to the details too. So I'm not sitting there saying, be like me. I'm just trying to let you know, giving you tips. Okay. So it looks like most of you have got the poll. Looks like a couple of you aren't quite correct on that. The answer should be false. It does not have to be unique. That's the whole point of the last two examples. They weren't unique. You know what unique means? It means one answer. How many answers does this one have? It has 2 answers. It is not unique. Okay, moving on. Okay, I'm going to have to go a little bit faster here if I'm going to get through this. Guys, I have 2 more big ideas to get. I'm going to go faster now. This one here is actually easier than the last one, I think, in understanding. And here's what it's saying. And in fact, let me explain it here first. You see this function down here, it's kind of going up and down and up, right? And I don't know what it's varying between, but let's say at its lowest point, it's 8, and at its highest point, it's, let's say, 12. And I want to know what's the average value of that function. Well, let's just say that the average value turns out to be 10, which might be what you would guess in the first place, right? You would kind of guess that maybe it's going up and down, and the average must be kind of exactly in the middle for this curve, which looks sinusoidal, and you'd probably be correct. Remember, whenever we find the average of something, like if I had you guys in class, I'd say, okay, guys, how would we find the average, let's say, body weight of the students in this class? Well, we would add them all up, and then we would divide by 30 or however many students there are, correct? That's exactly what this formula is doing. What is an integral? It adds things up. That's why we talked about what a summation is. And then what are we going to do with it after we add them all up? We're dividing by however many things there are. So let me say that again. This formula is essentially saying add up all the area and then divide by how many things we've added up, which is the length of the interval. Now, this is different than what we just did on the mean value theorem for calculus or for integration. This is simply finding the average value of the function. Let me do an example. Find the average value of, oh, wow, looky there. It's the exact same equation that we just did. So this is actually going to be much easier because we already know what the answer is. What is the integral from -1 to 2 of x squared plus 1 dx? What is that area? Well, we found a few minutes ago, if I'm not mistaken, I think we said it was 6, didn't we? Is that right? Okay, great. So I already know what that is. Now, the only thing new on this problem, and by the way, this is for the average value, I got to do 1 over 2 minus -1. This is the A, this is the B. So the final answer is just 1 over 3 times 6. So the answer is 2. Now you might say, wait a minute, Mr. Allen. You just told me that this is different than the mean value theorem for for integration. It is. Remember, our answers back then when we did the mean value theorem was, I think, -1 and 1, wasn't it? The other thing that you have got to keep in mind on this particular example, and I just chose this one to save some time, is this curve is symmetric. There was some symmetry there. And that symmetry kind of comes into play here. But this, I think you guys would agree. Would you not agree that that was much easier than what we just did? Even conceptually, I think that's easier to understand. So again, the formula is simply the integral and then times it by 1 over b minus a. That's all there is to it. And what that's telling us is for this function, when we go from -1 up to 2 for the x value, so we're talking about this part of the curve right here, it turns out that the average value of that function is 2. In other words, this part down here, I'll do it in green, this part down here was below 2, agreed? Whereas, and I'll do this part in, let's say, red, this part up here was above 2, wasn't it? So we have some of the curve below 2 and another part of the curve above 2, but on average, the value of the function was 2. All right, I'm going to again give you a few minutes here to try one on your own. And this one, I'm also going to encourage you to use a calculator. Okay, I forgot to put the calculator picture on here, but I'd like you to do the average value formula to find the average value of this function. It's a doozy. You would not want to try this one by hand. Calculator. All right, so let's go ahead and look at this one. I'm going to just start off by telling you the answer is 0.127. Hopefully I see some excited faces out there. I see a couple of excited faces. I get some people that are not sure. Okay, good. So that's the answer. To get the answer here, the average value is simply going to be the integral. Oops. Tell you what, I am not very good with this thing. And then I got to do 1 over pi. And then you're going to integrate this thing from 0 to pi. And then we're going to plug in our function here, cosine theta to the 4. This is how you would write it in your calculator, if you know how to use your calculator, times the sine of theta d theta. You would just type all that in your calculator and you'll get this answer. And just to let you know, here's kind of what that curve looks like. If this is theta and this is h of theta. Oops. Why it doesn't want to write there. Curve kind of looks like this. Kind of comes up, comes down, gets really close to the x-axis, and then it does it again. Kind of like this. By the way, you have to zoom in order to see that with your calculator. This is something that I've noticed over the years. Students don't spend enough time kind of verifying answers. They just get answers. They don't really know what they mean. So I would encourage you to graph these things and compare them. Okay. Questions on that one? If you have questions on the calculator, that's fine too.
Where does the 1 over pi come from?
So remember that here we've got to do 1 over b minus a, integral from a to b, f of x dx, right? This is b minus a, and that's the interval we're talking about. So in this particular example, oops, I went too far. Here's a, here's b. So you got to do 1 over b minus a, which is 1 over pi minus 0, which is 1 over pi. So that's why that's there. Does that make sense? Okay. Any other questions? All right, let's move on. Okay, we're doing good. We got 15 minutes left. Remember, I'm going to try to do 60 minutes of my thing. And actually today I'm going to go over, for those of you that are interested, I will either take questions on the quiz review, or I've also got some practice problems that involve some of the stuff we've been doing today if you're interested. So you're not required to do those things, but those last 30 minutes is support time. So anyways, so theorem 14 or 4.14, this is the net change theorem. And it says if f prime of x is the rate of change of a quantity, capital F, then the definite integral of f prime from a to b gives us the total change or the net change. And you might say, well, wait a minute, Mr. Allen, this just pretty much looks like the fundamental theorem of calculus part 1. It is. What this is telling us now, though, is we're going to be able to use this on applied problems, which is what the AP exam is going to emphasize, particularly on the free response. These are applied problems. In other words, real life problems, not just, hey, find the area under this curve. I'm going to do an example of an applied thing involving particle motion. Oh, actually, you know what? I just remembered I have one more poll I wanted to give you guys. So if you wouldn't mind, here's a quick poll. Should be very easy for you. And now we're going to look at this. I'll give you a second to do the poll. By the way, most of my polls are just to, are you kind of paying attention? If you're not paying attention, it's okay, but it's just nice to know. Okay, good. So it looks like most of you know what's going on, although some of you are not responding. So there you go. That's it for the poll. Okay. So would you guys agree it's probably better to be in class physically than, yeah. I know it's hard, guys. That's why I'm trying to like do the polling. The polling isn't really like, I'm not grading that. It's just, hey, you know, is Luca paying attention? Is Hayden paying attention? The questions aren't really to try to like stress you out or anything. And by the way, if you get something wrong, please don't worry. I'm not going to be like, oh my gosh, I think less of you. Just try to pay attention, okay? Take some notes. Okay, anyways. So we're going to do some applied problems here, and this is going to involve that net change theorem. It says the velocity, by the way, that's the rate of change. That's what velocity is. The velocity of a particle moving along the y-axis is given by, and then I'm giving you the velocity function. It says, what is the displacement of the particle on the time from the interval 1 to 4? And then B says, what about the total distance traveled? So first of all, displacement essentially is the net change. And you guys probably, actually I shouldn't say that. If you've taken physics, you probably already know what I mean by displacement. All's displacement means, in fact, let me draw a little bit of a picture here. So this is the y-axis. And I've got some particle, I'll do it in green. I got some particle on the y-axis. We don't even know exactly where it's at. But we just know that this particle is either moving vertically up or vertically down. And the position of this particular particle is not given. The only thing that's given about this particle is its velocity. So if I want to find its displacement, I just got to use this net change theorem. So all I need to do for displacement, I'll just abbreviate it as DISP, is equal to the integral from 1 to 4 of V of t dt. Now, guys, this is V of t. I'm not going to write it in there. I could, but I'm not going to. And do you guys mind if I just kind of skip the step where we actually figure out what the answer or how to get that answer? You could do this by hand or you could use the calculator. But I'm just telling you that the answer here is 48. You could find the antiderivative, which would be t to the 4th minus 3t squared minus 54t. Plug in from 1 to 4. You'll get an answer of 48. Can you guys live with that? Can anyone tell me, what does this answer mean? Very important question.
The area under the curve or the displacement?
We're not talking about area under a curve right now.
The distance it ended from where it started?
That's exactly right. Exactly right. So what this 48 is telling us is that that particle, ended somewhere up here, 48 units from where it started. So this is, let's say this is the starting location. And then its ending location up here is 48 units, and I'm going to call it north. Okay, because we're talking about vertical, right? If this had been a negative 48, what would that mean? That's right. It'd be 48 units south of where it started. Does that make sense? Now, I want to ask you a question. This velocity is a curve that is above and below the x-axis. In fact, let me just show you that curve here. Oops. And I've actually got some more data in here I forgot that I put on there. So I'll get rid of that in just a second. So here's the curve. And remember, I think I said from 1 to 4, didn't I? This is the velocity function. So here's my question. Let me do this in purple. You see this portion of the velocity here? Would you guys all agree that's below the x-axis? Which means it's negative. Which means what direction's the particle moving?
South.
South. Because the velocity is negative, that tells us it's going south. Now let's do this in green. You see this part up here? Would you guys all agree that's above the x-axis? And we're talking about velocity. It's positive. What's that tell us? Well, it tells us the particle's going north. Okay? Now I'm going to come back to this slide. So the second question I had right here says, what's the total distance? Do you think the total distance traveled is going to be more or less than 48 in this example? It's going to be more. Because the particle actually, let me do it in purple here, the particle actually went down and then it came back up before it got to that final place where it stopped. So how in the world are we going to figure out the total distance? You definitely want to add this to your notes. Total distance is equal to the integral from a to b of v of t dt. Does anybody know what I'm going to add? This, by the way, this looks exactly like what we just did there, right? Does anybody know what I'm going to add to this to get the total distance? I'll give you a hint. This curve over here, this positive and this was negative. How do I make the negative stuff positive? You do the absolute value of the velocity function. This is what you need to know. Please make sure you include this in your notes. You will need it in this class. You will need it on the AP exam. Total distance is simply the displacement with absolute value around the velocity function. In other words, it's making anything that's negative, in other words, going south, positive so that we can get the total distance here. Now, in this particular example, I'll do it in, let's do it in purple. The total distance is going to be calculated from going from, I think, what did I say, 1 to 4? 1 to 4, absolute value of 4t to the third minus 6t minus 54, absolute value of that. Now, I would love for someone to take some time to figure out how you would do that one by hand. And you can. I'm going to leave that for another day. We're just going to use I would just use my calculator for this. In fact, that's what I did. You can do it by hand. You'll get an answer of 165.971. That is the total distance that the particle traveled. So the particle went down, but then it turned around and it came back up. And then it finished off right there. And by the way, I should note, we have no idea where the particle started. If I said, where did the particle end, you would have to know where it started. The only thing we know is that it was displaced by 48 units north, and we know that its total distance is 165.971 units. Okay, does anyone have any questions on this applied problem? This is just one applied problem. There are many others that I could have done. I wanted to do this one in particular because particle motion is something that is often tested on the AP exam, and I also test it quite a bit too. It's obviously important for you guys to understand particle motion. I think that brings us to the end of the presentation. So at this point, I think I'm going to go ahead and give you guys the exit slip, and I'm going to stop recording. And the rest of this period, there's a couple of options.